Okay, so next topic is rates of change. And we're still in 3.3. So when we write just dy dx, right? So that of course means a derivative, right? It's a derivative, but it also means change of y, right? So derivative also is change of y with respect to x. Okay, so we could, I don't know, maybe I'll give you an example using physics, right? So if I write ds dt, so that would be change of position with respect to time, in time. So change of position in time. And another example, so that also could be this is also velocity, right? Instantaneous velocity. So let's write instantaneous velocity. Velocity. And yeah, if we could also do dv dt, right? That would be acceleration. So change of velocity is acceleration, right? Change of velocity or acceleration. And yeah, the function of position, right, would be just s of t. Right, so that'll be, so I'm going to just kind of translate that, calculating that first derivative into maybe something more applicable physics, right? So that s of t, right? So this kind of equivalent would be f of x, right? So maybe I'll write it above. So this is kind of like f of x. Where's that blue? F of x. Okay. So, but in our case, right, if we're in the land of physics, so this is a position of a particle in time. Okay, and then, right, the equivalent of, let me write that S of t plus delta t. Right, so this would be equivalent of what we've seen before as f of x plus h. Okay. Right, so this is basically a position at some new time, right? So some time, that delta t is basically some time past, right? And that's a new position of our particle. So position of a particle at a new time. Right, so that new time is that t plus delta t. Okay, so now if we want to, for example, calculate average velocity, and we would take the change in position. Right, so basically kind of like slope over change in time. Okay, so let me illustrate it. Right, so let's say, let me just draw a quick graph. Right, so we have this is so on the y-axis I have s of t, right, so position, and on the x-axis I have time. Right, so that that formula, let me write that formula first. Right, so I would take s of t plus delta t. I don't want to get too much into it, right? Plus delta t minus s of t. And then over delta t. Right, so basically what we're doing here is that should have made this picture bigger. Anyway, so yeah, so this will be our t, right? Oh, I know what to do. Okay. So then the distance, right? So that's my delta t. Okay, and then that other coordinate of that other point, the x coordinate, will be t plus, so t plus delta t. Right, so I did the same thing with those, right? There was before I had x, and this was, and this was x, this was h, and this was h plus x, right? And then, so now this is s of t, right? So okay, so I have s of t on the y-axis, and this one is s of t plus delta t. Okay. Yeah, so we have, so now if we're calculating the average velocity between those 2 points, I'm doing the slope of that secant line that connects those 2 points, that intersects those 2 points. So that's average velocity, but of course in calculus we don't do average velocity, right? We do instantaneous velocity. And I kind of mentioned that at the beginning. So instantaneous velocity. Okay. So basically, the only change, right? The only change that there is that there is a limit in front of it, right? So that velocity will be limit, right? And the delta t will approach 0, right? Just like with that h, right? So in a sense, right? I'm bringing that point, this point, right? Gets closer, kind of, right? I'm sliding that point towards the other point so that this delta t gets smaller and smaller, and well, it basically approaches 0. Right? So that instantaneous velocity will be a limit with delta t approaching 0. And then I have, right, I have the same formula, so s of t plus delta t, and then minus s of t. Okay, let me do it again. S of t over delta t. All right, so this is a formula for instantaneous velocity. Okay. Okay, so let's do an example that illustrates those concepts. So example, I don't know. I have in my notes I have example 8. All right, so let's start with the picture, and yeah, I think I can draw it here. Anyway, so there's a diver, and yeah, let me try to draw the diver. So diver is jumping of the board. Arms raised and ready to jump, and yeah, here's the water. Okay, the distance between the board and the board, the water and the board, is 32 feet. So this is, let me make it a different color, maybe yellow. Okay, so 32 feet. Okay. And yeah, this is water. Okay, so what we need to do, and the diver, like the initial velocity, right? So the diver jumps up, and that's kind of the direction. It's vertical. It's vertical, right? I drew it a little bit under the angle, but initial velocity is 16 feet per second. All right. And the question is, when does the diver, or calculate, maybe let's write calculate. When the diver hits the water. Okay, that's the first task, and then at what velocity? All right, so we're going to need some equations. So position of a falling object. Is described by a formula. That's a formula looks like this. So S of t equals 1 over 2. Then we have g, that's a gravitational constant. Then we have t squared. Then initial velocity times time plus initial position at 0. Okay, so let me maybe just kind of describe those values. So gravitational constant, and gravitational constant, yeah, usually it's given in meters per second square. So this is an acceleration, 9.8 meters per second square, or in feet per second square, so negative 32. I think that's what we'll use in that example, feet per second square. Okay, then this was t is just time, right? I'm not going to write it, initial velocity. And S0, that's initial position. Okay, so we'll simply plug in we have an equation, plug in the values, and yeah, we'll figure out what that time is, right? So I'm going to maybe I'll copy that equation. Yeah, and I will add plug in those values. So S of t, and so I have that half, and then we'll have the gravitational constant. That was, let's use that. We'll use that this value 32, right? Because we have that initial position was 32 feet above the water level, right? So that's negative 32 t squared. Okay, then we have plus that initial velocity was 16, right? Let me show it to you. Okay, so we're here. So this is the initial position, initial velocity, and then we have that gravitational force constant that was 32, negative 32 feet per second square. All right, so where are we? We're here. So that is 16t. And then that initial position was 32 feet. So 32. Okay, and then let's simplify a little bit. So S of t equals negative 16 t squared plus 16t plus 32. Okay, so the diver is going to hit water, right? And then his height above the water is going to be 0, right? That's when he or she falls in the water. Okay, so I'm just going to, right? So this is, in a sense, this is like y, right? This. All right, so we could pretend this is y when y is 0, right? Height, then the diver touches the water. Okay, so at this point, I'll factor negative 16 out. Right, so I'm assuming that height, right, above the water is 0, and then we'll calculate when that happens, right? So I'm just trying to solve it for t. Okay, so I have t squared minus t and minus 2. Right, just factored 16 out. So now I will factor this, right, this expression. I hope it's factorable. So two numbers, when you multiply them, they would multiply into negative 2, and you add them to negative 1. Right? So that's how we factor. We can, right, we can use this as this little x, and then this value is a times c, right? So t is a is 1, and c is negative 2, and then this value is b. Right, so negative 1. So those numbers will be negative 2 and 1. Right? When you multiply them, they give you negative 2. When you add them, they give you negative 1. Okay, so we have that negative 16. And then, right, I'm putting that 1 and negative 2, right, these two numbers. Yeah, it's factoring, right? You guys, I hope you're familiar with this. So t plus 1. And t minus 1, minus 2, sorry. Okay, so now if I solve it, right, I'm just kind of figuring out when this whole expression is going to be 0. So that's going to happen for t equals negative 1. and or t equals 2. So since t is time in seconds, so I cannot have negative time, right? So this, I'm going to discard this solution and just keep this one, right? So the diver hits the water after 2 seconds. Okay, so the diver will touch the water after 2 seconds. Okay, so that was, we answered the first question. The second question was, what is the velocity, right, when that happens? Okay, so velocity, velocity is the, basically, well, the derivative, right? So that was the derivative velocity. So let me write it. Okay, so velocity, let me show it to you. All right, so basically velocity is change of position in time, right? So over here, talking about this derivative, so right, ds dt. So I'm taking this, right, so what we'll do, we'll take this equation, right, equation for position, and we'll take a first derivative of it with respect to t, right? So think of this as f of x, right, or this as y, right? So this basically is, this is like dy, right? So now, right, I'm going to write, right, so it's going to be d over dt. And now I will put that equation for that, for s, right, for s of t. So that was half, and then we had negative. Let me use that, the one after we simplified it, right? So that was, I think, negative 16 t squared. Then we have plus 16t plus 32. Alright, so I'm taking derivative with respect to time. So now it's just the same, right? The same idea. So I'm taking that 2. This is going to go to the front, and then we'll subtract 1. Okay? And then derivative of this is just 16. Alright, so let's do that. Okay, so that equals, so 2 times negative 16, negative 32, plus 16. Right, so this is our formula for velocity, right? So v equals, for instantaneous velocity. Okay, and then we're calculating the velocity or speed of the diver when he or she hits the water, right? So that t was 2 seconds. We plug it in. So v, velocity, equals negative 32 times 2 plus 16. Okay, so we have velocity. Okay, so it's negative. So 32 times negative 32 times 2 is 64 plus 16, negative 48. Right, so we have negative number because feet per second, because that vector points down, right? The diver just falls down. Okay, anyway, so let's write down the answer. So let's put instantaneous velocity. Of the diver at t equals 2 seconds is negative 48 feet per second. Okay, yeah, so let's do a couple more problems. This time just kind of interesting and strange derivatives. So example 9. So find derivative of something like this. F of x equals x times absolute value of x. Okay, so let me just remind you that when you have absolute value, right? So this is not absolute value, right? This is x times absolute value. But if the function was, let me write it as a note. So note. So if I have f of x and just absolute value of x, so this function has no derivative at 0. So has no derivative at x equals 0. And because we have this graph that looks like this, right? And at this point, right, if this is axis, if these are the coordinate axis of x and y axis, x and y axis, right? So there's this point, right, at the vertex of this graph, that simply we cannot find slope, right, at that particular point. I'm talking about this point here. Okay, so this one doesn't have a derivative. Well, the question is, does this one have a derivative? And well, if so, what is it? And we're finding the derivative at x equals 0. Okay, so let's try to figure out what's going on. Right, so I have this f of x equals x times absolute value of x. So let's see what's happening. So if x is greater than 0, right, so I'm plugging in numbers that are bigger than 0, then our function is just simply f of x equals x squared. Okay, and then if I calculate the derivative of that, right, so f prime would be 2x. Okay, so that's the first case. The second case, if x is less than 0, right, then f of x would be negative x squared. Okay, and then the derivative will be negative 2x. Okay, so this is what's happening, and we're trying to figure out the slope of the line tangent, right, to the graph at 0. Okay, so yeah, we have when we have a point given, right, we usually would use that definition with C. Okay, so that would something like this. With limit with x approaching 0. Okay, so that C is 0. Then we have f of x minus f of c, so f of 0, divided by x minus c, or x minus 0. Okay, so yeah, let's see what we get. So I have a limit with x approaching 0. So the function, right, so I'm looking at this. The function is absolute value of x times x times absolute value of x minus f of 0. So if I plug in 0, I get 0. And then the bottom is x minus 0. Okay. So essentially what I have is, right, so limit x approaching 0, x times absolute value of x. So these two will cancel out, right? So we have limit, and then we have absolute value of x. And at this point I can plug in that 0, so we get 0. Okay. And well, technically, right, we could simply take that 0, right, that x, right, and plug it in here or in here. Well, both cases we would have to. Anyway, but I wanted to remind you that definition with C. Yeah, if we look at the graph, let's look at the graph quickly. Right, so it was something like this. So we had 4, right, if x's are positive, so that's gonna be just x squared, right? So parabola this way. And if those x's were negative, right, then we had this parabola. So this was negative x squared. This was, wait, where can I write it? Is there space? There is space. So y equals x squared. Okay, and what we did, we calculated the slope. We found derivative, calculated slope, right, of the line tangent to the graph at 0, right? So that's the line, and you see that slope of the line is equal to 0. This is a horizontal line. Okay. Okay, so I have one more example for this section, and this is example 10. And yeah, let's look at something like this. So where does the graph of so f of x equals x cubed minus 3 have a horizontal tangent? Okay, so yeah, let's look at the graph of this. I think something's not right. It's supposed to be x cubed minus 3x. So x cubed minus 3x. Alright, so let's look at the graph. Okay, so it's something like this. So it goes down, then goes through the origin, and then down. Right, so you see that the horizontal tangents will be in those two spots, right? and in those two spots, slope will be 0. So basically that means that their derivative will be 0, right? So f prime of x will be 0. Right? So same thing here. All right, so what we need to do is figure out the derivative, what the derivative is, and then make it equal to 0 and solve it. All right, so I have, let's find the derivative. So f of x, so it's x cubed minus 3x, and that's the original function. So now derivative f prime of x, 3x squared minus 3. Okay, so now we have the derivative, right? We're going to make it equal to 0 and solve it. So 3x squared minus 3 equals 0. So we have 3 x squared minus 1 equals 0. So yeah, if we solve it, we have those 2 points. So that's x, or actually let me factor it first. So x plus 1, x minus 1 equals 0. So we solve it and we get x equals negative 1, or x equals 1. Okay, so these are those x's for which the function have a horizontal tangents, right? Because derivative is 0. Okay, so this is 1. Yeah, what if we changed it a little bit? So how about yeah, something like this. So g of x, so very similar. So x cubed plus 3x. Okay, so if we calculate the derivative, it's going to be 3x squared plus 3. And now we make it equal to 0 and try to solve it. So 3x squared plus 3 equals 0. Factor 3 out. X squared plus 1 equals 0. So you guys see that now we can't solve this, right? So and we can divide it by 3. Yeah. So I would get x squared plus 1 equals 0. So this is not solvable, right? I get x squared equals negative 1, right? So the solution is not a real number. So the conclusion is that this function doesn't have any x's, any places where the tangent is, the slope of the tangent is equal to 0, or we have horizontal tangents, and that's because, right, when you look at the graph of this function, okay, so it looks something like this. Okay, so y equals x cubed plus 3x. Okay, so that's it. That's the end of this lecture, 3.3. And yeah, we'll move to, I think the chain rule is the next, or product rule. Anyway, see you next time.